geology and geochemistry of the granitoids of the northern part of Adamawa Massif, northeastern Nigeria. And I must say that my presentation will differ a bit from the general pattern of climate change from what you've been saying. It has less to do with climate change. It is purely geological. The presentation is intended to take this format. Sorry. To take this format, the introduction will be followed by field relation and lithology, then geochemistry, and finally summary and conclusion. Yeah, Nigeria is situated within the Pan-African mobile belts, as you can see there, and lies between the West African Craton to the west, the Taurus Shale to the north, and then the Congo Cratons to the southeast. Now within the country, two distinct provinces of basement rocks have been recognized. These are the western province of the schist belts and the eastern province dominated by mecmatite, gneisses, and the Pan-African granitoids. Now, opinions are divided over the evolution of these rocks, of the Pan-African granitoids. The first opinion is that suggests that the rocks are products of tectonic processes involving a continental collision between the West African Craton there. The first opinion is that the rocks are products of continental collision between the West African Craton here and then the Pan-African mobile belts. And that opinion is based on recognition of a suture along the eastern margin of the West African Craton. Then the second opinion is that the rocks resulted from aggregation of crustal blocks, such as islands, and then the older continental fragments. And that opinion is predicated on the close association of calc-alkaline volcanics, ultramafics, and mafics associated with some major fault system in the western part of the country here. Now, even though the first opinion has been widely accepted, some workers have observed that the Pan-African granites that extend into Nigeria here and then the neighboring Cameroon, a distance of over 1,500 kilometers from the suture, cannot be all related to the same subduction zone. And then there has been paucity of geologic information on the rocks here. This is where the Adamawa Massif is situated. This is the Adamawa Massif. So it is in light with all this that the present study takes advantage of excellent exposures of the Pan-African granitoid in the northern part of this country, of the Adamawa Massif, to provide information on the field relation and lithology of the granitoids, to provide major trace and rare earth elements data on the rocks, and to use both the field and geochemical data to provide an insight into the petrogenesis of the rock. And now to achieve this objective, the study was divided into two, the field relation and lithology, and then the geochemistry. And for the time constraint, I will just quickly go through the field relations and lithology, and then we go to the geochemistry. The area was mapped at a scale of 1:50,000 naira, and the study showed that the area is underlain by porphyritic granite, equigranular granite, fine-grained granite, granodiorite, mecmatite, and then subordinate pegmatites. The porphyritic granites are the most abundant and most extensive As you can see here, I'll just quickly go through it because of time. And there's gradational contact between the porphyritic granites and the fine grain and the equigranular granite. As you can see here, the contacts are gradational. Then we also have few sharp contacts between the rocks. Then the equigranular granite are mostly massive with top blocks on of miltel materials, just as you've seen there. And then the fine granites also have angular enclaves. Within there are fine grain subangular granites enclaves within the equigranular granites. Then you have low-lying fine grain granite with numerous fractures. Then you have also gradational contrast between the granodiorite and granite. You have the granodiorite occurring as massive and elongated plutons in the area. Then you have the migmatites of restricted occurrence. Then you have the pegmatite, which cross-cut most of the rocks units in that area, Now, inferences. According to Chappell and White, 1978, these field characteristics, such as the massiveness of the rocks, with little or no foliation and subangular to subrounded shaped enclaves, paucity of banding, presence of large phenocrates are all suggestive of I-type granitoids. And the dominance of gradational boundaries suggests that the rock units may be genetically related to a common source. Now, this is the geology. Then some samples were now selected, believed to be representative, were selected and subjected to microscopic studies. And the porphyritic granite sample shows holocrystalline textures. We have the hibidiomorphic granular texture in the equigranular granite. We have hibidiomorphic granular texture with essential minerals of hornblende, plagioclase, biotite, microcline, and quartz. Then the migmatite has also holocrystalline texture with subhedral and anhedral microcrystal of microcline and quartz. Then you have fine grain granite with cross-height twinning in microcline. Then the chief points: the granites are characterized by plagioclase, biotite, and microcline with accessories sphene, apatite, and zircon. The granodiorite is characterized by hornblende, plagioclase, and biotite plus accessory magnetite. These are typical mineralogical features of I-type granitoids. Now, the geochemistry. The samples believed to be representative of the different rock units in the study area, which were shipped to ARC Lab, Canada, for the determination of major elements using lithium metaborate, tetraborate, fission ICP whole rock package. Then the trace elements using fission ICP MS package, and then the rare earth elements using fission ICP MS packages. And the analysis are tabulated here. We have the analysis for major elements. And then we have the CIPW normative minerals calculated from the analysis. Then that is followed by trace elements data. Why I'm just going through this is because the data in this form may not make much meaning to us until we plot them. Now we have the rare earth element data, and then we have some major and trace element ratios that are calculated from the analysis. Now, to characterize the rocks, now the classification scheme of Cox et al. 1979 was chosen, and that group our rocks, they are into granites and granodiorite fields when the alkalis were plotted against silica. Now, attempt was also made to probe the chemical affinity and probable source of these granitoids. And here again, selected oxide pairs and ratios were plotted on binary and trivariate variation diagrams. Now, at a plot of potassium oxide versus silica, group our rocks in the high potassium calc-alkaline field, as we can see there. Then when the alkali ion magnesium trivariate diagram was used in plotting the samples, now it shows the Calc-alkaline signature with marked alkali enrichment here and suppressed ion enrichment. Now when the aluminum saturated index was plotted against aluminum, against the ratio of aluminum and then the alkalis, the samples were divided between the metaluminous and the peraluminous fields, as we can see here. And now when niobium was plotted against silica, the igneous parentage now is clearly indicated with most of the samples in our I-type granite field here, and only one sample within the A-type. Now the chief points and inferences: the metaluminous to weak peraluminous character, the smooth calc-alkaline trend, the broad spectrum of composition spanning from mafic granodiorite through felsic granites are all chemical features of I-type granitoids formed in a subduction-related setting. Now also probed the evolution of the rocks, various hacker-type variation plus of selected major oxide using silica as the fractionation index were adopted. And so when silica was now plotted against the magnesium oxide, we have coherent trend or clear liquid line of descent showing the magma evolution from the most primitive rock there to the most evolved rock here. And when silica was plotted against calcium oxide, we have coherent series to still showing the magma evolution trend here from the most primitive rocks to the most evolved here, with clear absence of separate groups. Now when silica was plotted against iron oxide, we still have similar trend here, the primitive ones, then you have the most evolved or rocks there. And when silica was plotted against manganese oxides, a similar trend was shown. When silica was plotted against titanium oxide, we have a similar trend showing magma evolution from the most primitive to the most evolved rock types there. And then when silica was plotted against phosphorus oxide, we still have the same similar trend there. And when silica was plotted against sodium oxide, we have the linear trend with some scattering here, but the scattering is actually typical of sodium oxides. And when silica was plotted against aluminum oxides variation diagram, we have similar trend, we have the same trend there with a little scattering there, but still typical of aluminum oxides. And now when silica was plotted against potassium oxides, we now have a kind of positive correlation trend from the most primitive now here to the most evolved igneous rocks there. And when titanium now was plotted against the ratio of aluminum oxide and titanium oxide, we have a clear curvilinear trend typical of magmatic crystallization differentiation. As you can see here, a curvilinear trend typical of magmatic differentiation. So the regular inter-element variations within and between the rock units, the linear or near-linear hacker-type variation diagrams with clear absence of separate group, the curvilinear trend in a plot of titanium oxides against the ratio of aluminum and titanium oxide are all typical features of cogenetic rocks related by magmatic differentiation process, probably fractional crystallization. Now, to probe the tectonic settings, stress elements were plotted against one another as suggested by Pearce et al. 1984, Harris et al. 1986, and Wallen et al. 1987. And such plot of rubidium versus the sum of yttrium and niobium divided our samples between the within plate granite field and ocean-rich granite fields there. Now, when niobium was plotted against yttrium, the samples were divided between the within plate and syn-collusional granite fields, as we can see there. Then when tantalum was plotted against ytterbium, the samples were shared between the within plate granite field, syn-collusional field, and then volcanic arc group, but with most samples in the within plate granite field. And now, when the ratio of rubidium and 10 hafnium and then tantalum times 3 were plotted, all the samples were felt within the within plates granite field. Now, when niobium was plotted against silicon oxide, almost all the samples plot in the orogenic granite field, as we can see here in the orogenic granite field. Here we have the non-orogenic granite field. All right. Sir. Now the chief point, the figures indicate orogenic character with within place syn-collusional signatures. Collectively, the diagrams suggest that the granitoids are orogenic formed in a within plate syn-collusional tectonic environment. And now to compare the rare earth element abundances of the granitoids graphically and study the degree of fractionation. The concentration of the rare earth elements were normalized to their abundances in chondritic meteorites, and such normalized rare earth element for the granitoids showed fractionated rare earth element patterns, as we can see here, with a more fractionated light rare earth element pattern, a nearly flat heavy rare earth element pattern here, and a significant negative EU anomaly, as we can see here. Now, the rare earth elements for the granitoid normalized to average continental cross showed fractionation in strontium, barium, titanium day, and phosphorus relative to rubidium here. So inference, then strongly fractionated rare earth elements with enriched light rare earth elements and nearly flat heavy rare earth elements, the increasing negative EU anomaly from the granodiorite to the granite are all indications that the fractionation of basic melt to yield silicic magma was dominated by the removal of plagioclase and thus produced significant negative EU anomaly. Now, summary. The field and petrographic data indicates that the northern part of Adamawa Massif is underlain by porphyritic granite, granular granite, fine-grained granite, granodiorites, migmatite with subordinate pegmatites, and that the rock units are separated from one another by predominantly gradational contacts, and that the essential minerals are mostly hornblende, plagioclase, biotite, K-feldspar, and accessory apatite, fen, and zircon. That the rock units are characterized mostly by mafic enclaves. Then the geochemical data indicates systematic decrease in all the major oxides from granodiorite to the granite except silicon oxide and potassium oxide, which rise sympathetically. Then progressive decrease in trace elements from granodiorite through granite except rubidium. Then strongly fractionated rare earth element with enriched light rare earth elements and an increasing negative EU anomaly from the granodiorites to the granites. And that with calc-alkaline trends with metaluminous to weakly metaluminous character, I-type affinity with within plate orogenic signatures. Then conclusion, based on the fields and petrochemical characteristics, the granitoids are probably I-type generated in a within plate tectonic setting. and genetically related to a common source by fractional crystallization, dominated by the removal from the melt of hornblende, plagioclase, biotite, k-feldspar, apatite, sphanes, and zircon. Thank you. Any questions?
Good afternoon. Has the collisional environment that you've been studying led to formation of petroleum reservoir basins that Nigeria is so well known for, in your opinion? And could you show us on the map, the first map that you put up on the slides that had the geology of West Africa, could you show us where the petroleum basins are located approximately and how extensive they are?
Sorry, come again, where the what is located?
Oil, gas, petroleum basins.
Okay, in Nigeria. Now, the oil, gas, and petroleum in Nigeria are located here within the Niger Delta. Here, within the Niger Delta, this way they are. But exploration right now is going on in the Chad Basin around here. Around here. So this is where the petroleum is located within the country, in the sedimentary basins. Yes. But what I've just talked of is the crystalline basement, the basement rock, the granitoids. Thank you.
Thank you.
Well, thank you very much. Yeah, thank you, sir. Yeah, thank you.